Have you ever wondered what exactly happens inside your body when your senses are completely hijacked by modern technology? Imagine this for a second. You're standing perfectly still on solid ground, but your eyes are screaming at your brain that you're plummeting down a steep drop at 80 miles an hour. It's literally a biological collision between the physical world and the digital world, and honestly, the way your body responds to this shock is absolutely fascinating.
Welcome! In today's Explainer, we're exploring the adaptive brain from virtual to reality. We're going to take a journey from the baseline, everyday physical biomechanics that simply keep you standing upright, all the way to a high-tech disruption of your senses using virtual reality. By looking at a really incredible clinical study on postural stability, we'll see in real time how incredibly fast our nervous system can learn, adapt, and basically rewrite its own rules to survive.
Okay, let's dive into this. Here's our roadmap for today. First, the postural control system. Second, virtual reality sensory mismatch. Third, the VR roller coaster study. Fourth, adapting to the illusion. And finally, sleep, memory, and recovery.
Let's start with Section 1, Postural Control. We'll look at the macro view of how our brain naturally keeps us stable in the physical world, which is something we entirely take for granted right up until it stops working. To maintain what we call postural control, keeping an upright, controlled posture against gravity, our bodies actually rely on a brilliant symphony of three distinct balance systems. You've got the visual system for environmental cues, the vestibular system, which sits deep inside your inner ear to sense gravity, and the somatosensory system, providing physical feedback from our muscles and joints. Combined, they achieve postural equilibrium. Think of these three systems as a complex biological symphony, and your central nervous system is the master conductor. It constantly takes in all these diverse sensory inputs, integrates them, and fires out precise motor commands to your muscles so you don't just tip over. Now, let's shift our focus to Section 2, Sensory Mismatch and VR Disruption. What exactly happens when this delicate biological symphony is completely hijacked by immersive technology?
Well, this brings us to a phenomenon known as sensory mismatch. It occurs when the central nervous system is unable to distinguish between accurate and inaccurate sensory information from one or more of these balanced systems. This disruption results in dizziness, unsteadiness, or poor balance. Essentially, your highly evolved brain is getting completely hacked by a screen strapped to your face. Imagine you put on a VR headset. Your eyes are telling the master conductor in your brain that you're on a wild, twisting roller coaster. But your somatosensory and vestibular systems, your legs and your inner ears, are reporting that you are standing perfectly still in a quiet room. This conflicting data creates a massive stress test for your central nervous system.
And that leads us perfectly into Section 3, the VR roller coaster study. Researchers actually decided to measure exactly what this kind of mismatch does to the human body.
So they took 28 healthy young adults and put them through a highly controlled testing methodology. Step 1 was the control tests. The subjects simply stood quietly on a highly sensitive force platform with their eyes open and then with their eyes closed to establish their normal baseline sway. Step 2, the VR shock. They underwent 5 repeated VR sessions watching a 120-second immersive 360-degree roller coaster video with 10-minute rests in between. Finally, Step 3 was the measurements. The researchers used posturography to measure the physical sway and energy their bodies exerted on the platform, and EMG sensors to measure the electrical activity and co-contraction of their leg muscles.
The setup to capture that data was brilliant. EMG sensors were placed bilaterally on vital postural muscles, like the tibialis anterior on the front of the calf and the gastrocnemius on the back. They also placed them way up on the hips. By recording the electrical activity here, researchers could measure the co-contraction index. Basically, they were looking for stiffness. You know, when you're thrown off balance and you just instinctively tense up? Your body's initial strategy, especially during an unpredictable task, is to tense opposing muscles at the exact same time to stiffen your joints and stop you from falling. We literally call this a stiffening strategy.
The results from that first VR session were absolutely staggering. When we compare the baseline to the initial VR shock, you see that during the control stance, subjects showed normal sway and energy usage. But the moment that VR roller coaster started in session 1, the high-frequency sway energy, those fast, panicked, corrective movements to maintain balance, spiked by an incredible 481%. At the same time, the co-contraction of the hip muscles increased by up to 92%. The subjects' bodies were rigidly stiffening up and their feet were microscopically wobbling, burning massive amounts of energy as their nervous system desperately fought the VR illusion. The brain was just totally overwhelmed by the sensory mismatch.
Which brings us to Section 4, Adapting to Illusion. We've seen the physical shock, But now let's look at the nervous system's rapid ability to adapt to a hostile new environment. Over the course of the 5 sessions, the participants' bodies began to figure it out. The total energy the subjects used to keep themselves stable in the anteroposterior direction, meaning swaying forward and backward, was at its absolute highest during that chaotic first session. But by session 5, that wasted energy dropped by a massive 37%. Muscle co-contraction and stiffness dropped significantly as well. What the data reveals here is the nervous system actively abandoning that inefficient stiffening strategy and actually optimizing its feedback control.
The mechanism behind that drop in energy is fascinating. Researchers concluded that repeated experiences can initiate sensory reweighting, increasing resilience to visual disturbance. Now, sensory reweighting is such a cool biological process. The master conductor in the brain realized that the visual information from the VR headset was completely unreliable. So in real time, the brain literally turned down the volume on the visual system and turned up the volume on the somatosensory and vestibular systems. It learned to ignore the eyes and trust the feet. This quick motor adaptation is a phenomenal example of the brain learning on the fly.
Let's move to Section 5, Sleep, Memory, and Recovery. We need to bridge the narrative from real-time motor learning to the biological mechanisms of how the brain actually consolidates these new skills.
The crucial point is summarized perfectly by the researchers. Major functions of the higher levels of the nervous system are learning and memory. Learning is simply the neural mechanism by which we change behavior as a result of experience, exactly like we just saw with the VR sensory reweighting. But here's the catch. Short-term memory only persists for minutes. To make this adaptation a long-lasting form of resilience, the brain requires processing time. Specifically, areas like the parietal cortex, which integrates the sensory context, and the frontal cortex, which directs the motor execution, need time to firmly lock in these new neural pathways.
And that locking in process is deeply tied to our brainwave frequencies. When the subjects were in that VR headset, visually processing a wild roller coaster and rapidly reweighting their balance systems, their brains were likely firing on all cylinders in high-frequency gamma and beta waves, the states for high concentration and learning. But to actually consolidate that short-term motor adaptation into a long-term memory, the brain needs to transition down. It needs to power down through alpha and theta waves, all the way into delta waves during stage 3 deep sleep.
Let's see how this builds into the restorative power of sleep. It's a biological imperative. As we cycle through non-rapid eye movement and rapid eye movement stages, incredible things happen. The body conserves the energy and metabolism that was so heavily taxed during that high-stress VR exposure. But more importantly, sleep reverses the physiological degradation that occurs while we're awake, and it converts that short-term motor memory, that newly learned ability to ignore the VR illusion, into a long-lasting memory. Without sleep, the central nervous system simply cannot maintain homeostasis, and it definitely can't permanently remember the balance adaptation we just witnessed.
It's truly amazing to see the hard data on just how hard our bodies work to keep us grounded, and how fast we can adapt to completely artificial environments. But it does leave us with a pretty compelling question. As modern technology increasingly hacks our senses with immersive virtual realities, is your nervous system fully equipped and rested enough to adapt? Thank you so much for joining me for this explainer. If you found this breakdown of human biology and technology as fascinating as I did, make sure to like, share, and subscribe. Press the bell icon to get notified when we release more explainers. And if you're ever dealing with physical therapy needs or require emergency pain relief treatments from sensory overload or otherwise, be sure to visit the clinic linked on the screen. See you next time.